Now that we've looked at inverse matrices and looking at all of those different things in order to use matrices, we're going to be talking about partial fractions. So with partial fractions, it's really a decomposition of a polynomial or a function. So for instance, 5x minus 25 over x squared minus x minus 25, not minus 25, minus 12. We're going to decompose this and separate into the sum of two fractions. And the reason why is because you're taking a linear and a quadratic, and we don't necessarily want that when we're looking at a graph. We want to look at a linear and a linear, or a quadratic and a quadratic. And so as you can see, the top is linear and the bottom is quadratic. So if we split it up into an addition of two linear products, it's going to be easier to see. And so that's what we're trying to do here. So with that being said, you decompose this by factoring the denominator, and so that you can use your quad program on this and find your factors right away, no big deal. So when we look at this, we get a over x plus 3 plus b over x minus 4. And that's what we're looking at initially here. And again, I got those factors just because of my quad program. That's all I did there. So in order to keep going with this, x minus 25 has to equal a times x minus 4. It goes opposite because, we got to have a combined fraction in order to technically add, which is what you're really doing here. A times x minus 4 plus b times x plus 3. So what I'm going to do here is I am going to go ahead and distribute this. So I get ax minus 4a plus bx plus 3b. So I'm going to go ahead and combine my like term and factor out information that I need. So if I look at this ax plus bx minus 4a plus 3b, I'm going to factor out any information I can. So with the x's, it's a plus b times x. And this the negative 4a and the 3b, I can't really do anything about. So from here, now that I have it factored out, the first one that matches up with the x matches up with the number in front of the x. So really, a plus b equals 1. And then the second part, negative 4a plus 3b, matches up with that negative 25. Now, if I look at this, I technically have a system, and I can use matrices in order to solve the system. So if I take the inverse matrix there and multiply it by that 1 over 25, I'm going to get 4 and negative 3. So now I have solved my matrix using inverse matrices. I just plug that in, multiply it, the good stuff there. 4 gives me A, and negative 3 gives me the B. So I can go back and take this and put it all the way up here into this original. So that my final answer then, my decomposition of partial fractions, is 4 over x plus 3 minus 3 times x minus 4. we'll work with this. We got another example here. Actually, we have another two, hopefully, in which you're going to catch on to the pattern here. This time, I do have a quadratic in the top. It is a quadratic over a quadratic, but again, it's easier if I work with linear. And so that's what I'm going to be doing here on this. So the first thing I want to do is the fact that this one isn't linear is I want to go ahead and divide. I'm going to go ahead and divide it truly by what it is. So I get x squared minus x divided by, technically it'd be the other way around, negative 2x squared plus 9x minus 4 divided by that x squared minus x. So I'm going to go ahead and factor out, or go ahead and do my division. So I get negative 2, which we know, we take this negative 2 and distribute it, giving that negative 2x squared plus 2x. That way I can go ahead and simplify this down a little bit. So I get 7x minus 4. So what does this mean for me? What this means for me is that I've broken it down so that the top is linear. So I can go through and break it down just like I did in example 1. So right now I've got 7x minus 4 over x squared minus x equals negative 2 from the top here, plus a over, I'm going to go ahead and factor the bottom out, which is x and then x minus 1, plus b over x minus 1. Okay. So again, not working with the left side really. I'm going to go ahead and just kind of let that negative 2 hang out. I'm going to go ahead and take care of this part though, and do what I did from example 1. This one happens to be a little bit easier because it's just an x, it's not an x minus 1 or x plus 3 or, you know, whatever. It's just a singular x, which makes it easier. So you've got a times x minus 1 plus b times x. Again, that negative 2 just keeps hanging out. I'm going to go ahead and distribute, and I get ax minus 1a plus bx. I'm going to go ahead and combine my like terms. And because you've seen this, we're going to factor out the a plus b. So now I'm going to go ahead and set up my matrix. So we know that the a plus b has to equal the number in front of the x, which in this case happens to be 7. So the second one is just a negative 1a. I don't have a b, which is fine, and that equals negative 4. Well, if I look at this, I don't even have to use a matrix, a true matrix, or inverses, because this system is already solvable, because a, I can divide by that negative 1, is going to equal 4. Once I get the a, I can plug it into that top equation there in order to see that b is 3. So now I can write my true partial fraction as negative 2 plus 4 over x plus 3 over x minus 1. One more example here, and this time we're working with a cube, and again we're trying to get it down to a linear. So we've got 3x squared minus 5x plus 4 all over x cubed minus 4x squared plus 4x. So this one, because there's a difference with the x squared and the x cubed, I don't have to factor the top and divide it out, just because those are different degrees. Looking at this one before, it was x squared and x squared. So that was why I had to divide, is because I needed those degrees to be different. I needed the bottom, the denominator, to have a higher degree than the numerator. If you look back at the first example, we had x to the first in the numerator and x squared in the denominator, which is why we don't have to divide that top part. But I'm going to go ahead and factor for my decomposition here. I'm going to have 3x squared minus 5x plus 4 all over x cubed. minus 4x squared plus 4x. This is going to give me a over x plus b over x minus 2 plus c over x minus 2 squared. The reason why we have it technically it's an x cubed and this shows with the partial fractions an x to the fourth. The reason why we do that is because when you factor the denominator, it can be written as x times x squared minus 4x plus 4, or it can be written as x times x minus 1 squared. So because there's that difference, you have a factor of x minus 2, so you need to include that in both of them, and that's where that b comes from. Because technically, yes, you get that, you can break it down into x and x minus 2, but because you can factor it as two different ways here, both of these have a factor, both of these have a factor of x minus 2, and that's where this one comes from. Okay, I know that it looks kind of confusing because you're like, what happened? We've just factored it out to what it was, and that's why. Okay, so this one's a little bit trickier because you have three different things to multiply. We get a times x minus 2 squared plus bx. The reason why is because I'm multiplying by that x to the left there. X minus 2 plus c times x. I'm going to go ahead and distribute this, and I get ax squared minus 4ax plus 4a plus bx squared minus 2bx plus cx. It's okay if you can't distribute it quite that quickly. The x minus 2, make sure, as a reminder, that you break it down into x minus 2 listed twice to make sure you do that distribution correctly. I'm going to go ahead and combine my like terms, and I get a plus b x squared plus negative 4a minus 2b plus c times x plus 4a. From here, I'm going to go ahead and set up my matrix. I have a plus b equals, if I look back here, it equals a positive 3, negative 4a minus 2b plus c equals a negative 5. Then I have a 4a equals 4. So this one, I could set up an inverse matrix, but I can see here that a is by itself, so I'm already set up that I can just find a as 1. I'm going to go ahead and plug that into the top equation to get b is 2. When I plug a and b into the middle equation, I get c is 3. So now, as you can see, we've kind of used that same pattern throughout. Now I'm going to go ahead and write my final answer, and that's 1 over x plus 2 over x minus 2 plus 3 over x minus 2 squared. I know this is kind of fast, but I hope you guys can see that the pattern keeps repeating itself, such that the more that you practice this, the easier it's going to get because, like I said, the pattern repeats itself.